Hello, everybody, and welcome to the seminar on Mutex versus Semaphore. My name's Niall Cooling. I'm one of the founders and directors of Feabhas Limited, and I'll be giving the talk today, the webinar today. So first off, I'd like to start the session talking about the principles of quasi-concurrency. What this means is, in the sense, I'm trying to simplify it in dealing with a single processor solution. So rather than getting to more complex multi-processor or multi-core solution. So dealing with a single microcontroller and a single image. So we've got a linked image, we take an ALF file, created a bin file from that, and it's running out of flash. And in a normal traditional C program or C++ program, there is only effectively one thread of execution, which is main. That's our entry point to the user program. But what using a real-time operating system allows us to do is to create multiple threads of execution. I like to refer to them as like mini mains, each one acting as almost a main in its own right. Each thread of execution is a sequential piece of code, so we can follow it through, we can follow the path of execution through. And the purpose of the real-time operating system, using an operating system, is to give us some sort of time-sharing model. There are differing time-sharing models out there, but most follow what's called a priority-based preemptive model to allow us to swap and time-share between these different threads of execution. To understand what's going on, the need for mutual exclusion, we first need to appreciate when one of those threads of execution is running. Then we talk about the idea of a processor context. So if we abstract the processor architecture, the core architecture, then of course we need a program counter that is normally pointing at flash and working its way based on our instruction code and using branching to deal with any of our conditionals within that. So that's keeping track of where our program is. And we can follow that at any time. And of course, there is only one program counter for a single core. We'll have a status register that the main from a programming logic in there are the flags, and the Z flag, the 0 flag being the most important one. This is used typically for sort of branch equals 0, branch equal not 0 opcodes, which are mapped onto like our if expressions and our switch expressions, etc. So our control logic gets mapped on. And it's the flags that allow us to move around the code base as such. Importantly, in modern programming is a stack pointer. So stack pointers has a number of functions. The main thing is for function call parameters, so the arguments being passed for return values quite often are passed on the stack, and local values as well. But one of the major reasons for stack is to give us the potential for recursion as well. So functions being able to call functions within that. But that's most modern processors are going to use what we call a software stack and can use stack relative addressing. Finally, there are a set of program registers, and these are used by the arithmetical logic unit to perform our ALU operations, such as our adds and our substitutes and our conditionals in terms of comparisons, etc. And this is generic, and it will vary slightly from processor to processor, and obviously the use of the registers does vary between, for example, a RISC architecture and a CISC architecture like an ARM and an Intel. But fundamentally, this is what's going on. And as we're running through our program, then these are all changing. But then what we need to add to that is the memory system, looking at the memory system. And for a running program, so what we'll call a process, a program and execution, we also have to include the read-write memory. And we can break the read-write memory down into a number of sections. Of course, there is a single stack for main. There is possibly a heap, obviously most embedded or a lot of deeply embedded certainly don't use dynamic memory, malloc, so we don't have a heap, but we could possibly have a heap in there. And then we talk about statics. A lot of people refer to those as our global variables, and they are broken down into two groups. Those that are uninitialized, that, for example, will go in what's called the BSS area if you're using the GCC compiler, and they're the zero initialized globals. And then we have initialized globals as well. And there's just a reason they're broken down to do with the way the system initializes before main. So we call those generically, those two things are static data, and they'll all read-write memory. And finally, we'll have our image and possibly our constants would normally be in read-only memory like flash. While my program is running, that we can talk about that being the process context. But to swap between units of execution within an individual program, then simply all we need to do is have a model where we can save a current image of the register set. So the processor context as such. So we need a mechanism where we can store this away. Now, the simplest model used by a lot of operating systems is to push all of the registers onto the stack and purely store the stack pointer and then bring in another stack pointer. So what this first tells us in a multi-threaded multitasking system is that every task has its own stack. So rather than one single stack like with main, for each unit of execution we're going to use for each thread of execution, they will all have their own stack. So that model there, that stack is broken down into a number of stacks within that. And the mechanism for doing this, again, will vary from operating system to operating system and core to core, but fundamentally we're saving this away. And this information sometimes is stored away in something called the task control block. So the stack pointer may reside with the task control block. So each task has its own task control block. So simply context switches, we stop where we are. So we finish the current cycle. We save the current register set away to RAM into this task control block. We go and find the next job that needs to run. We find its stack pointer. We pull all of those registers into the image of those registers into the core, and then we start running again. So the basic context switch is a really, really simple idea. But as soon as we get multiple threads of execution running within the same process, within the same program, sharing the same memory, then we can end up with this concept of a data race condition. So this is a very simple example, and actually this was taken from a real system that I was involved with many, many years ago, where the engineers I was working with saying we keep losing messages, and we're not quite sure why. And it was a simple case where there was communication between two threads through a sort of buffer. We represent as a stack here, and there was a common count within that, so that was in shared global memory, and one thread is incrementing that and one thread is decrementing that. Now, as an example here, we've shown a typical sort of assembly you'd possibly get from an ARM Cortex system if we were doing C or C++ increment decrement. And the typical model is we've got to go and get the address of the memory and load that into a register. And then the ARM uses this relative addressing model. So the square brackets say take the address stored in that register and load that. So we'd be loading the contents of the address stored in R4 into R1. So R1 will contain our count. We add 1 to that, and then we store that back out to memory again. So you can see there's 4 opcodes there to do a basic plus plus. And the converse of the minus minus is same process set this time. We're substituting from that. Now the key is the context switch itself can appear between any assembler opcode. And this can lead to this classic data race condition. And the problem is this is because it's a temporal model, we may do lots of testing and never actually encounter this. So the model is we've got one thread running, it's got its own register set, so that this is the real register core running, it's got this. So it's gone out to the memory system and loaded that count value into our register R0. We now decrement that because it's the consuming thread to 2. But before we've had chance to actually store that back in memory, there's been a context switch. Now, of course, we've now saved those register values. We've saved R0 away into the task control block of the consumer thread, and we brought in the producer thread context. And as part of that, we restore R0 to the value it was in the producer thread last time it ran. And that doesn't really matter because what it's going to do now, of course, is fetch the count. And the count is still 3 in memory. We increment that, and then we write that back out to memory. So now it's 4 in the shared memory system. At some point later, we're going to context switch back. And as part of that context switch, we restore consumer R0 from what it was. So that's going to restore it back to 2. And our next opcode is simply going to store that, then write that out to the shared memory system. And here we can see, in effect, we've lost a message. Our count has gone from 4 to 2, where it should have really been at 3 at that particular point. So we normally refer to that as a data race. It's a race to get. And as I said, because it's a temporal problem, it may not always show up. Quite often you can do lots and lots of testing and never see this exact problem. So it can be difficult to create this type of problem and reproduce it when you're getting it in that system. So to deal with this problem, operating systems, we talk about, from an abstraction perspective, a model called critical region. So without talking about how it's being done, Semaphore, Mutex, it's like, what are we trying to do? And the idea of a critical region is simply saying we've got some sort of resource that is shared amongst threads, and we need a protection mechanism. We need to say, one, I'm accessing this resource. In our case, it's the count, and it's the stack we're working with, that we should only allow one thread to be manipulating that at any one time. Now, importantly, the entering a critical region, and normally that is done through an API to the operating system, some sort of function call. It doesn't stop a context switch. We mustn't stop that. We still want other threads to be able to run within that. But what it should do is when another thread tries to access that same critical region through the same API, the operating system will now block it. It will suspend it and hold it at that point. So that would allow my consumer thread in this case to run at some point, and it can finish its work. And it says, now I'm done with that resource. I can tell the operating system that I've left the critical region. So the important thing here is we're talking to the operating system saying I'm entering and leaving that region. And of course, that means at a later point, our producer thread can now run and finish it. So this idea of, so it's atomic where it can't be, if that makes sense. We can't actually have atomic operations at the processor level, so we have to tell the operating system we want to treat these as a set of atomic operations. Now, important to go back and look at where the naming terminology came from. And obviously the term semaphore is actually an English word and it goes back hundreds of years. But from a programming perspective, it's very much dated back to 1965 when Edgar Dijkstra wrote his first paper on cooperating sequential processors. And at that time, because of his background and being Dutch, he used these particular names that the P and V typically refer to for the entering and exiting of the critical region. And the P comes from the Neologism, prolonged to try and lower, and the raise, the increase. And this was very much based on a single binary token. And when you entered the critical region, you decremented that token to 0. And when you raised it back to 1 again. On the principle is that if you try and enter and the token is already 0, then you block until that count is available, that token is available, and then you can enter. So it comes in turn the binary semaphore. Only one thread can ever be in a critical region at one time, and this count model is only ever a 1 or a 0. So it gives us our binary model. So that's where the original binary semaphore came from, the work that Dijkstra did associated with that. And that gives us this model, this simplified state model, where we can only ever have one task, one thread running. And in the case that if that task is running and tries to wait, call the P operation, call the enter critical region, and it can't do because there's already another thread in that critical region, then it would go into the waiting state. And then finally, the V would take it out of the waiting state and move it back to the ready state. And then the operating system prioritization model would choose what actual thread continue to run at that particular point. So this is the common state model you'll see in all sort of operating system kernels in our particular system. Working with Dijkstra at the time, and actually some work that came slightly after his work with the Scholten work, and Scholten developed this concept called the counting semaphore. And unfortunately, when most people use the term semaphore, they actually mean the counting or general semaphore as it was. And this was used for a slightly different model. So here, the model Scholten was talking about is where we have a set of resources. And we can have, so rather than just having one token, a binary token, we can create a group of tokens, a pool of tokens. And while that pool is available, we can continue it to enter. So rather than being a critical region, it's saying we've got these number of things. So the analogy I'm using here, the example here, is if we have a set of spaces, parking spaces for a robotic car parking system, and we would start, and the initial state would be for the counting semaphore, there'd be the equivalent of a token, a count available for every free car parking space. And every time we wanted to park a car, we would just decrement that count. And that would always continue until we got to the point where, of course, every car parking space was filled. And at that point, any new cars that needed to be parked would have to wait until one of the parked cars had actually left at that point. So it's a slightly different model from the critical region in the sense that it's perfectly valid for multiple threads to conceptually be in this resource region. And it was designed for exactly that model, where we can have we have multiple resources, and as long as you can get one of them, that's fine. So it does play a slightly different model to the binary semaphore for that particular model. Now, the first time we saw these outside of general purpose operating systems like Unix came in the 1980s. In the 1980s, we started to see the first commercial real-time operating systems. There were a number around. I was lucky enough to work with Vertex at that time. There were things like PSOS, and so the early 1980s. And at that time, they tended to use the general semaphore for basic mutual exclusion. Some operating systems offer both the general and a binary. So, for example, the one I've used at the bottom is the FreeRTOS API. Probably FreeRTOS, the most widely used real-time operating system to date. And that actually has two different APIs, a semaphore create binary and a semaphore create counting, where you might find many operating systems don't differentiate between those two. They purely have a create semaphore, and that is most likely to be the counting semaphore model. Now, in a sense, you can use the counting semaphore as a binary semaphore if you only initialize it with one token. But as we'll see later, that isn't quite the same model, and it can lead to some subtle errors and subtle bugs associated with our particular system. So we're using semaphores in the sort of late 80s as we had the real-time operating systems. And then we started to see a number of different problems and issues through using a semaphore for critical regions. And these are the five I've listed here are probably the five core ones you may come across. So the first one is this concept of accidental release. And this comes to the fact that there is no actual pairing between the acquiring of the semaphore and releasing the semaphore. So the code example again here is using the FreeRTOS API, and that uses what's called a take-give model. So here we can see on the left, we've got the apps thread doing mutual exclusion, and it's done a semaphore take, and it's done the count decrement, and then done a semaphore give as a good citizen working through that particular code. So that's a correct use of a semaphore for mutual exclusion for a critical region. On the right, we've got the comms thread, and through some mistake, it could be a cut and paste error, it could be a commenting error, and this does happen. I've seen this happen firsthand, where the code there's a give in there without a take in the system. And of course, now depending on our type of semaphore, this will lead different types of errors. And the problem with a give is certainly for a counting semaphore, the give will always succeed. So we'll never have an error state because all a give really is internally doing is incrementing a count. And for most counting semaphores, there is no upper bound. A lot of them don't, even though you may create the counting semaphore with say 4 or 10 initial tokens, a lot of them don't cap that. They'll just keep incrementing an internal count. So quite often, if we had that code, we'd never actually see the error associated with it. So that's our first one. And of course, that's going to create some weird behavior where sometimes it works, sometimes it doesn't. So again, a nightmare to actually debug our system. The other thing a semaphore can't deal with is, from a design perspective, if the same thread called tried to acquire the semaphore twice. So it did it once, and this can happen normally because of some sort of library-based call. So if you acquired some sort of semaphore, and then within a library, that same semaphore has tried to be acquired again. Quite often it's done around locking to things like malloc, to dynamic if you do allocation. And it does happen. So here, for example, is an example bug that was reported in MySQL, okay, not real-time embedded, but just to show that these things do happen, where there's been a crash because of a deadlock waiting on itself. Some people argue this should never happen. It's a design issue, shouldn't be a programming, but again, that's a separate discussion outside of the scope of what we're dealing with today. But we need to appreciate that semaphores can't be recursively locked. And if you try and do that, you'll end up in this deadlock situation where everything suddenly starts locking up within our system. A more subtle one is the concept of deadlock through death. And this is where we have our thread that has got the semaphore, it's acquired the semaphore, it's in the critical region, and through some sort of problem within the code base, the thread has ended up crashing. So this could end up, for example, dereferencing a null pointer, going out of the memory system and accessing the memory incorrectly, or a program counter being misaligned and accessing an incorrect opcode. And if that thread crashes, then typical RTOS, an operating system, cannot detect the thread that has acquired the semaphore no longer running. And that means it can never be released. And that means then all further threads that block on that semaphore or try and acquire that semaphore will deadlock. They'll never be able to run again as such. So death detection is a really subtle one in there because, again, it's one of those types of problems that as much testing as you do may never surface. And of course, as soon as you go live, you may get that one. Finally, one that we started to see in the early 90s was, and this is quite well known now, is this concept of priority inversion. So priority inversion comes in when we start allocating priorities to threads, and the order of thread running is dictated by their priorities. So here we show a low, medium, and high priority threads. Now, in the initial state, we've got the high and medium threads in a suspended state. They may be waiting on some sort of timing-based model, some event from the real world. So the low priority thread has run, it's locked the access to the shared resource. We then, the medium and high priority become readied. And as soon as they're ready, the operating system, the dispatching engine of the operating system will compare the head of what's called the ready queue, which is a high priority task with the current running thread, and say, if it's a higher priority, we're now going to do a context switch at that point. So we're going to swap out the low priority task and we're going to swap in the high priority task. So we've done our context switch. And the first thing a high priority task wants to do is now try and lock that same resource. And of course, we can only ever allow in a critical region one thread in there. So naturally that then has to block. But because of our prioritization model, the low priority thread doesn't get to run because the medium priority thread is at the head of the ready queue. So the operating system will go and grab the medium priority and schedule it, do the context switch to it, and it will start running. And that means that the high priority task cannot run again until the lower priority task gets a chance to run to release that resource. And this can cause real problems. And the best documented one, if you've not read about it, the Mars Pathfinder, was a real problem that they discovered on the surface of Mars, which was exactly this problem. They were using a heartbeat model, so they're detecting that the high priority thread was being blocked for longer than was expected, and they were having to do a full system reset at that point. The final one to look at is this idea of semaphore as a signal. Now, with most people today working with real-time operating systems, this is the most likely way they're actually using a semaphore. And this, again, is how things have changed over the last 30 years or so. So semaphore signal is where, rather than using a semaphore for mutual exclusion, we're reusing the model to give us some form of synchronization primitive. So the simple example, again, the example here is we created a binary semaphore. Now, again, this is using FreeRTOS as an example. Now, FreeRTOS, when you create a binary semaphore, it's actually creating what's called the taken state. That means it doesn't have that internal count, that token. So it's got a count of 0 internally. So our thread 1 is going to run, and it does a take. And at this point, when it does a take, it's going to block because that internal count is 0. And it will stay in that suspended state, that block state, until thread 2 comes along and does a give. And as soon as it does a give, it increments that internal count. And by incrementing that internal count, the operating system will now wake up thread 1, remove it from that suspended state and put it back into the ready state. And depending on our prioritization model, either thread 1 or thread 2 will start executing, but both will be readied at that particular point in time. And the key to this model, is semaphore as a signal, is of course that the take and give are, from a code-based perspective, are now in different threads. So it's perfectly valid to have a take without a give in the same bit of code and a give without a take in the same sequential unit. So this makes it not obvious when I'm using semaphore as a signal or when I'm using semaphore for mutual exclusion. So if we compare those two examples in our system, so on the left, what we're showing is if we were using a semaphore for mutual exclusion, we can see that we'd have a pairing of a take and a give. So if thread 1 had done a take, thread 2 does a take, it will suspend because thread 1 is in the critical region. When thread 1 does a give, thread 2 will be readied and it will now have access to the critical region. But on the right-hand side, where we're using it for synchronization, then we can see that the take and the give are across the 2 separate threads. And naturally, this makes debugging harder because you can't look at a code base and say, hold on a minute, I've got to give without a take there. And also, if we've got these copy and paste type problems, again, it's not immediate from the code base. That's the actual problem. So what changed was, in the early 90s, we had the POSIX model came along, the pthreads model came along, and as part of that, it introduces a concept called mutexes. So mutex comes from mutual exclusion, the critical region, mutual exclusion, basically the same principle in that the critical region gives us mutual exclusion to a resource. And the mutex only added one very simple concept. And the key concept here is ownership. It really is as simple as that. So the basic and fundamental difference between a mutex and a semaphore is that we have, when the mutex, when we lock and unlock a mutex, we know which task, which thread is the locking, unlocking thread. And that then allows us to address a model, because the key to this is only the thread that locks the mutex is allowed to unlock it. So only the thread that has entered the critical region is the one to unlock it as such. So very, very simple change. It has a very minor performance implication on it. And it is trivial in the big scheme of things, but we always appreciate there is a slight performance difference in the two. But it really is as simple as that. So it's just this idea of it. So if we go back and revisit those 5 issues again in the context of using mutual exclusion, a mutex rather than a semaphore. So simply, and the most important one is that we can't get this accidental release. If we try and unlock a mutex that we didn't lock, then we'll get an error code. So as long as we're writing our code as it's shown on the right here, the comms thread, that as long as we're checking our return values from our unlock, then we'll clearly be able to check there's been an error on release. So we would hopefully catch that very early in our testing phase and certainly not let it propagate out to production-based code with it. So the benefit is you can't, let's say you can only unlock a mutex if you've locked it in that particular model. Now, because we have ownership, that then also enables the potential for recursion. And not all real-time operating systems, not all operating systems support recursive mutexes, but many do. And notice again with FreeRTOS, it has an API of a create mutex and a create recursive mutex. So it does differentiate between the two. So we need to be aware, or you certainly need to be very aware when you're creating your mutual exclusion primitive, your mutex primitive, is correct, getting the correct model for the needs you have. So the basic recursive model is the same thread is allowed to relock the mutex multiple times as long as it unlocks it the same number of times. So you can think of a nested model associated with that. We look at death detection. So here's our model for death detection. We've got task 1 running. It's got that mutex locked. So it's gone in and acquired the mutex. It's accessing the resource. Now, at some point, that task crashes. Because we can detect that there's built into the operating system, we can look at when a thread is aborting, when it's exiting the system. We can see, the operating system can see that the thread that owns the mutex is no longer active. It's gone out of that running state associated with it. And now we can have a model for passing ownership. And different RTOSs have different models. So you'd need to look at the details of your particular operating system. Now, many don't have anything. Many still don't do death detection, even though they have mutexes. So that's the first thing to check. Those that do some sort of death detection, there are 2 models you'll tend to see there. The simplest model is that the ownership of the mutex gets passed to the head of the waiting task, and that will normally be the highest priority task. So here we've shown it being passed to task 2. But normally when it gets access to the mutex, when it locks the mutex, it will get a slightly different error code indicating that yes, it's got access, but the resource is in an unknown state. So that means then programmatically we can start saying, okay, I can go and clean that resource or check the integrity of that resource, because it might, for example, be a structure with multiple elements, and we might want to check those multiple elements are all correctly in synced. So there might need to be some housekeeping done on the resource to get it back in a correct state for correct operation to be able to continue the system running. The alternative model is it just wakes all of the tasks up and they all back off and then all try and reacquire. They all get an error code basically saying you can't acquire the mutex, and then you need to have that programming model that none of them now have the mutex, but we know that we're in some sort of error state. So again, look at your operating system, look at what it offers, see what that particular case is. Now, the reason we didn't see priority inversion really earlier than sort of the late 80s, early 90s is because a lot of the early work and Dijkstra's work was around general purpose operating systems. And even though most general purpose operating systems like Unix at the time use a priority model, they all use a dynamic priority model. That means the operating system is allowed to, at runtime, choose to change the priority of each running thread. And this eliminates things like starvation, where a thread is not getting any access, not getting any work done. And because those operating systems come from what we call a fair share model, where you want, a historical model where multiple people are working on a computer, you want to give everybody a fair share of that computer. So with a dynamic priority model, you don't see this priority inversion issue. As soon as we move to a real-time operating system where we would want fixed priorities and heuristically we're setting those priorities up, then we can introduce the priority inversion problem, because what we don't want is the operating system changing priorities. Only we should be able to do that through a programming interface. Now, when this first surfaced, and we started to see this in the early 90s, there were a number of academic papers and a number of development that went forward to try and address this. The most common one you'll see implemented by operating systems that do is support priority inheritance is something called the basic priority inheritance protocol. So there's a generic term called priority inheritance that covers both of these. But the basic priority inheritance protocol is the one that most operating systems implement, mainly because it's a simpler model. Some do support the immediate ceiling priority protocol. So there is a term called ceiling priority protocol, and there actually are 2 variants of that. But of those 2, the immediate ceiling priority, again, is the most common one. So the PIP is the dominant one by a long way. You may occasionally see the ICPP, and there are, say, this other one, which is probably more academic. So how does it work? If we go back to our model, it's a very simple model. Back to the situation before that, we've got to a position where we've got a locked resource with a low priority thread. We've got a high priority thread has done the context switch. It's now trying to access the resource. The important difference in the model, when the high priority tries to lock the resource, obviously the operating system, we can't have multiple threads in the critical region. But what we now do is we can look at which thread owns that resource, has access to that resource, and we give it the priority of the current running task. So in this case, the low priority thread inherits the priority of the high priority thread. And that means on the ready queue, you can now see we've swapped around the medium and the low and the medium threads on the ready queue. So now the low thread is at the head of the ready queue because it's got the priority of that high. So that's where I'll turn from. And that means we now suspend the high priority thread as we would expect, but importantly, the low priority thread with the current dynamic high priority runs. It gives it opportunity to now release that resource. And as soon as it releases that resource, it unlocks the resource. It goes back to its original priority, that particular model. Now, as soon as it unlocks the resource, the high priority thread goes from the suspended state to the ready state. It will go to the head of the ready queue, ahead of the medium priority task. And that means we'll get our context switch. The operating system will see that there's a higher priority task on the ready queue than the running thread, and it will now context switch that out as normal. And that means the higher priority task then can acquire the resource through the mutual exclusion and can continue. So there's still going to be a delay. We can't avoid that whenever we have critical regions. But what we want to do now is minimize the delay of a high priority task being blocked, waiting on a low priority task to release that resource. And like I say, this is very widely supported by most modern day real-time operating systems in our side. Because the Mutex is purely used for critical regions for mutual exclusion, then there is no confusion, or there should be no confusion, between using mutual exclusion and doing synchronization with semaphores. Now, some of this will be down to the API of the operating system. Now, one of the things I dislike slightly about the FreeRTOS API is that it still uses a give-take model. So it sort of confuses these terms in my view. So we have a semaphore create binary, a semaphore create counting, and then a semaphore create mutex and a semaphore create recursive text. Now, again, maybe this is a very personal thing, but I really dislike mixing the term semaphore and mutex in the same. They are two completely different concepts. In that, when many of the operating systems will have semaphore APIs and mutex APIs, which I think is a slightly better model. Also, the thing that with that model where you have a completely separate semaphore and mutex API is you'll see that the mutex API will normally have a lock unlock function call, and the binary semaphore will have more of a give-take model. Again, FreeRTOS, I think, to slightly confuse the issue, uses this generic give-take model, even if you're working with mutexes. And from a maintenance perspective, it still gives opportunity to cause confusion. Again, that's a very personal thing, and I'm sure Richard Barry will disagree with me on the API design. But like I said, I would like to see, and I prefer to see, complete separation between mutual exclusion and mutexes, lock and lock, and binary semaphores, or semaphores and counting semaphores with a give-take model. We just want to, where we can, reduce the potential for accidental mistakes. And the more obvious the API, the less potential we have, less opportunity we have for those particular errors associated with it. Many operating systems have said don't support recursion. Again, FreeRTOS does, an example, but certainly older ones. And be careful that you have two APIs. So even within FreeRTOS, we have the create mutex and create recurve mutex. So we've got to get the right one for the type of work we want to do. FreeRTOS supports the basic priority inheritance protocol, as do most real-time operating systems. So our VxWorks and our Nucleus and our ThreadX, etc. So I'd say it's a very, very common model today. And I certainly wouldn't use a real-time operating system that didn't support some form of priority inheritance today. So that would be a very, very risky thing to do. And I think you're dealing, and that's again why you really don't want to be writing your own operating systems today, because you've always got this potential within that. Interestingly, FreeRTOS, as far as I'm aware, does not have any form of death detection. So we do have the potential for deadlock if a thread does crash, if it's acquired a mutex, for example. I said many do. Actually, pthreads doesn't, but surprisingly, the Windows API does, which was quite a shock. But some of the RTOSs will do death detection in there. So again, do look at your real-time operating system. Do dig into what the mutex interface is and what the semantic model is and the syntactical model as well between those particular two. So hopefully you can see now that the mutex, by using a mutex and separating it from the semaphore and used exclusively for mutual exclusion, then and critical regions, then we don't get into this issue, this potential problems associated with the semaphore. However, the mutex on its own still doesn't address certain basic issues that we'll always get whenever we're programming. So here's a first example, a very simple example. We've got a team of people working on this. We've got a ADC interface, so we've got some sort of analog interface, and we're reading data in through an ADC, and we've got a couple of threads running there doing some algorithmic work, and then they're spitting out values over the DAC, over the analog output. And we've got two engineers working on two different threads, so the work's being partitioned. One engineer is working on the control thread, and they've been told that when they're doing their sort of pipe and filter model, that they must lock the ADC, lock the DAC, get the data in, and do that. And we want to do that all in one operation. So we want to get the work for performance reasons. We want to lock the two resources, read the data, do the algorithm, write the DAC out, and then release them again, because we don't want any jitter in that period. And then we can say for the system identification, again, they're being again the same remit. We've got to lock the two things, but subtly they've programmed it slightly differently. The control thread does a lock ADC and then a lock DAC, and an unlock ADC, unlock DAC, where the system identification has done a lock DAC, lock ADC. So they've done them in the inverse. So at the surface, they've both done what they're asked to do. The two engineers have done that work, but there is this subtle. Now, when we do all our testing, of course, it all works fine. So we start running, we can see the control task comes along, locks the ADC, it locks the DAC, it's doing its work, and the SI is a higher priority, so we get a context switch. It tries to lock the DAC, but to stop that model, again, it's going to get blocked. The control task can now go back and do its work. When it's finished with those resources, unlocks the ADC, unlocks the DAC, that waits at the SI, and then it can then, like I say, reacquire the DAC, reacquire the ADC, do its work, and then finally unlock those. And as again, that's our error-free situation. All our testing, that works absolutely perfectly. But then we get this subtle timing error where the control task has locked the ADC, but before it's had potential to lock the DAC, it's had the opportunity, sorry, to lock the DAC. We've ended up with a context switch. So the SI task to start running, and it's locked the DAC. And the next thing it then tries to do is lock the ADC, and it can't, because that's locked by the control task naturally. So it's going to go into a blocking state. The control task now starts running, and the next thing it then tries to do is resumed. It tries to lock the DAC, and it can't do that because that's locked by the SI task. So this is quite often referred to as a deadly embrace. So the control task is dependent on a resource that is currently locked by the SI. The SI is dependent on a resource that currently owned by the control, and we're never going to get out of this position. So we've got this deadlock, but of course the rest of the system may continue. Yeah, the display task is running, it's happily locking its own separate resources associated with that. So again, a subtle timing type error that may not show up during testing. Now, for this to occur, there are four basic conditions we have to be aware of. So first off, naturally, we're using some form of mutual exclusion. So I think that's a given if we've got shared resources. The next one's the most important, this concept of hold and wait. And what we're saying with hold and wait is a task can hold a resource while waiting for another. So that means that we can do a lock, we can acquire a resource and then try and acquire another resource. And if we don't, we're allowed to block at that point. So that's what hold and wait. We can hold one resource and wait on another. We have some sort of circular dependency. So from a design, again, people will get into this issue, whether it's a design issue, but certainly some of these circular dependencies can be subtle because they may not just be between two tasks, there could be a number of tasks that have a chained-based circular dependency. So it's not always as obvious as those slides show within that. And then finally, no sort of resource preemption. That means that we can't force a task to release a resource. And normally this is the case with most operators. You don't have any form of ability to force a thread that owns a mutex to release that mutex. So for this deadly embrace, this circular deadlock, as we call it, to occur, all of these conditions may apply. Now, note that the bubble says that the ceiling priority protocol eliminates the possibility of hold and wait. So that's why some designers will argue that the ICPP is a better inheritance model than the priority inheritance protocol. It's a more complex model to implement, and that's why most operating systems don't support it. It takes some more work up front, high priority, to get it right. But yeah, it uses a very different model, and in terms of the fact that priorities are given to a thread as soon as it locks it. We get inheritance at the point of lock, not at the point of wait. But again, you can read about that offline to look at the two different ones and appreciate it. So one of the benefits of the ICPP is you can't deal with this deadlock situation. So if we're most likely using things like the priority inheritance program, for example, with FreeRTOS, then the one that we can address most easily, obviously we can address the design issue of circular waiting, but more simply, we can address the hold and wait one. And the way we will quite often address the hold and wait one is you will see through an API some sort of try-lock or timed lock model. Now, try-lock is a very simple model where when we try and lock, it either can lock it or it can't. So it's a back off straight away. So it has no blocking capability. So if we try and lock and it's busy, we just get an error code back straight away, and then we have to deal with that and choose our own. And the principle there is if we can't, so on the second lock there, we do a try lock. If we couldn't acquire our second lock, The principle is that we'd fail that, we get the error code back, and what we'd immediately do is unlock our other one as well. So it's either we can lock both of them or neither of them, and we work out some back out model where we'd come and try. So we'd only move on if we could actually acquire both at the same time. So the try lock gives me that. The timed lock is a variant of that. As you can guess by its name, the time lock has some sort of timeout capability. So most operating systems will give you a time frame. It may be in things like milliseconds, or it may mean a concept called ticks. Ticks are normally mapped onto either milliseconds or tens of milliseconds, as an example. So again, here is a FreeRTOS where it has ticks to wait. And you can create a try lock by using a time. Most operating systems will support a timed lock of 0. And if your time lock of 0 means it never waits. Unfortunately, there are some operating systems out there where a time block of 0 means infinite. So do be careful and check the API of your operating system. So you may not see a try lock, you may just see a time block, but a time block of 0 will simulate a try lock model. Also, there I've shown the new C11 API, and that also is inherited in C++11, is they both now have a Mutex model within their API. Now, again, that's not normally supported by deeply embedded compilers, but for example, you're working on a Linux type platform, then you have Mutex is now built into the language, and they support both the try lock and the timed lock model within that particular model. So that's addressed the deadly embrace model. The other problem we can get is that everything we've talked about so far is based on what I call being a good citizen. Is we're relying on the application programmers to construct and use critical regions as we need them to be. So on the right hand side, we've got the consumer thread doing the Mutex lock and lock as we would now expect of a well-crafted mutual exclusion critical region. But on the right-hand side, there's nothing to force me to use the Mutex. So the code that's been on the right-hand side is still accessing that common, it's accessing the stack, it's accessing the count, but not going through the Mutex API. And how do we enforce it? So the argument generally is that the use of a Mutex, in a sense, is too lower level primitive for application programming. Now, this was first addressed, interestingly, you can see the date on this, 1974, by Tony Hall, very, very famous author, and he introduced a concept called a monitor. And the monitor, again, is a very simple principle. And it's just that we put the locking mechanism and the resource together as a single conceptual, a single cohesive unit. So that means that the application level, the task level, we're only seeing a very simple API, and the tasks themselves should never have to be making direct calls to things like Mutex lock, Mutex unlock, or Semaphore locks, etc. So if we take our stack example using FreeRTOS as an API, what would a monitor stack look like? So the key about a monitor is you build them. They're not part of an operating system primitive. They're not part of the API. Is you tend to build them. And the way we build them, so here we've got our example, we've got our stack, and we want from an application perspective to simply offer a push-pop type model. We have an init function that's creating the Mutex, and then we'd have a Mutex as a static member. So again, remember, static in C is going to give me internal linkage. That gives me encapsulation. So that means that all of the stack, the count, and the Mutex are all hidden from the application code. They're not within the linkage model. So within our push and our pop, we now can write the take, get, give model to form the critical regions. And we never have to worry about the accidental misuse or bypassing of the interface to get at the stack from the application level. So this is the basic principle of the monitor. And it's one of the design patterns, the basic real-time design pattern where we're at. Now, there is an extension to this, a thing called condition objects. I'm not going to get into today because they're for synchronization. But you'll see also that condition objects give you a blocking capability within the critical region. So this is really more a design consideration, is when you're looking at your design, you're using threading and you need shared resources. It's trying to think of this conceptual model of monitors and building monitor-based objects so that we decouple the application programming also from the API. So we decouple ourselves from the API of the operating system, which gives us, again, portability. And we're never in a case where we can bypass that particular interface. So that's really all I wanted to say today about the Semaphore and the Mutex. And hopefully now, based on what I've said, there's this very simple clarification of what is a Mutex and what is Semaphore. And it's such a simple model, is that the Mutex has this idea of ownership. That is all it really comes down to when we get down to it. And by having this ownership, it then allows us to do a number of different things now to address some of those issues, such as the recursion. We can implement priority inheritance, potential death detection. Now, again, remember, your operating system may not necessarily support any of those. So it may not support recursion, it may not support priority inheritance, and it may not support death detection. I would be wary of using operating systems that don't support at least most of those. Certainly priority inheritance. Ideally, you would like to have death detection within those. Build monitor patterns. Think about monitor patterns when you're doing your design, when you're doing your coding. And finally, I hope you now understand the difference between a binary semaphore and a counting semaphore, and appreciate how most people use them today for signaling, for synchronization, rather than mutual exclusion. And it's a pattern. Semaphore is a signal as a form of pattern, but it's a sort of misuse is probably too strong a word, but it sort of is a variant of the API and reusing that particular API in that section.